reasons I really like interstellar flight as a challenge is that it's far enough out, not many people work on it, which gives you plenty of elbow room to be innovative and break from the norm on how you do things. Now, most of you, when you think interstellar flight, you'll probably remember these science fiction images that come to mind, and also some of the legacy messages that came from that fiction as to why we might want to go out there. And, you know, there certainly is a primitive or primate reason to that. But when it comes to the reality, and if you want to know what is the reality, how do you find that out? Well, one of the lessons I've been learning along the way is if you want to see into the future, look at the pioneers. And these are the pioneers that led to rocketry, which is now, well, old hat. And the other thing here is pioneers are people, not organizations. So, you know, you don't look to MIT or NASA or ESA or whatever. You find the people that are the pioneers. And to give you an idea of what's different about pioneers and other innovators, okay, refinements is what innovators do. They make sailing ships better, or they go from Apollo to what was referred to as Apollo on steroids. Pioneers break from those norms and change things, like taking steam power and making steamships, or in the case of my favorite ones, exploring unfinished physics and trying to make space drives. The other way is to find them, is to look to the publications, because pioneers do publish. You can find them in the journals, but they'll write about the edgy stuff. They'll be on the comfort zone of their peers, but they're also self-critical. The type of work that they do, you can see that they really understand what the challenges they're facing. It's not just wishful visions, and it's not sales pitches. It's more honest work. And also typically, until they succeed, they're the underdog. So there's a certain amount of, they need help to succeed. So on interstellar flight, and as I was learning this through my career, by the way, when I retired, I had over 31 years in because I started when I was 18 years old. I started doing this stuff on the side and did a website about explaining what was the real edge of the science on the goals of warp drive. And then through the networking and finding other people, we started Interstellar Propulsion Society, and that barely got started before I was asked to create a NASA program on looking at such things as faster than light and controlling gravity, which really surprised us because we thought the threshold for that would be actually having a working device. Also, that got the attention of Walter with his STAR labs, and eventually, as government funding goes, it goes in fits and starts. The funding ran out, and my boss said, well, why don't you go back to school and learn something interesting? And I did a degree in physics entrepreneurship at Case. And basically, it's like, well, you know, I also learned from the NASA thing that that wasn't the best place or the best way to do it. This was a combination of a number of things. And then also one of the absurdities at NASA, I couldn't rely on volunteers. That's illegal. But I relied on volunteers a lot, and it's just a normal way of doing things. So it's like I wanted some more flexible means to do it. So I started the Tau Zero Foundation, which is a nonprofit. And I retired in February so I could devote more time to this. And lo and behold, out of the blue, in a press thing, there was an announcement that DARPA, and that was mentioned before as a United States military research thing, is funding NASA Ames to the tune of $1 million to study the business case of a nonprofit organization to do pioneering research into interstellar flight and educate students and inspire students. So I'm going to be meeting with them, but that's kind of weird timing, so I have to look into that. Just a short thing about what Tau Zero is. This idea of finding the pioneers and helping us collaborate is basically what it's about at this stage. And so I've got about 40, and it's not just scientists and engineers, but also journalists and artists, because sharing this to the public and inspiring is a part of it. And we're chipping away at this. We're not going to say we're going to build a starship tomorrow. We're going to chip away at the unknowns to get to that. But the other thing is this is a long-term endeavor to make interstellar flight happen. So we also want to enable the pioneers, the young ones now, to give them the reliable information, to inspire them, and to point them where they can go to school and what they need to do to make a career in this. So that's basically what we're doing. Now to get back to the actual interstellar flight things. What's out there? Carl Sagan used to say billions, and hopefully maybe that even means money someday. But the other thing, as of just December 3rd, a few days ago, the total count of exoplanets, that means planets around other suns, has reached 500. Now, there's no Earth-like planets in there yet, but that's kind of promising. So to ask yourself, where are potentially habitable planets? Well, one of my collaborators, who's actually in the audience today, Claudio Macone, started looking this at from a statistical point of view. And the short answer I want you to pay attention to on that curve is that first knee in the curve, which is near 25 light years away. Basically, it means that when we think about designing spacecraft to reach habitable worlds, 20 light years is kind of our minimum. And if you really want to go out, we should really be aiming for like about 90 light years. Now, a light year is a time of distance, and light is the fastest thing we know, but in terms of astronomical space, it's slow. It's really slow. For example, the distance between our sun and the Earth, it's 8 minutes long, and that's very small on this scale. Anyway, to move on from that. Oh, the one other thing I forgot to mention on that chart, if you're worried about running into habitable situations, the estimates are now is that we might not run into any of those until we go more than 500 light years out. So hopefully there will be some habitable planets that we can plunder. Now, when it comes to the question of practical interstellar flight, there is no one reason. As a matter of fact, and this is why we want to cover the span of possibilities. I mean, practical is according to what you consider important. If you want to do what we can already do today, that's one thing. The Voyager 1 and 2, they've been en route since 1977. They've just now reached 0.002 light years, and by the way, our nearest neighboring star is over 4 light years away, so, you know, we got a ways to go, and that was 30 years. But you have this scan, you know, this is the most affordable, which you could really do without spending that much, but it's going to take you millennia to get to our nearest neighboring star. Well, if you go up to the next step technology, which is usually where the hot debate is about what's the right choice, well, you know, you can probably get there in centuries, and it's going to cost a whole lot more. And if you push it to the next level, the edge of technology, well, you can probably get it down to decades, but I'm not sure what it will cost yet. And if you really want to go there within the short attention span of people, you need to break the light speed barrier, and that goes into the realm of the unfinished physics. So I'm going to give you short examples of all these. As far as the simple solar sails, there's been books written about that, and the top 2 guys there are also part of my network that explain how solar sails work and what you can use them for. Another example is that rather than trying to do an interstellar mission in full to where we reach out, what are the intermediate learning missions we can go? And this would be going out 10 times farther than what our Voyagers have done so far to turn around and look back and take advantage of the gravitational lensing of our own sun, and to put a communication buoy there for future interstellar missions. Another one, and this is one that has been very active, Project Icarus, which is son of Daedalus. It's a sequel to this interstellar mission study done by the British Interplanetary Society in the late 70s. And what they're doing is they're revisiting that, since there's been many technological innovations since then, to see what that might do. And there's about 20 other people on their team, and what's nice here is that these pioneers are actually young, which is refreshing. To give you a scale of how big that vehicle was, if you remember the Apollo missions going to the moon, that was that huge Saturn V, that's how big the Daedalus vehicle would be. So they're re-examining that. And it's a 5-year study. They're into year 1. They're actually on schedule and on budget. And by budget, it's a volunteer organization. Everyone's chipping in on their own. They're going to look at what can actually be built if you extend the technology to its edge, and also what would it take to make that real? What are the steps we'd have to do? What are the things that would have to make? And mostly, this isn't a sales pitch to say this is possible. This is to deliver the reliable information to show where do we really stand now. And as an example of what will it take to be real is looking at the business case for mining helium-3 from the clouds of Uranus. And so that's the level of detail that they're going into to try and scope this out. Now, this next Starship example, these technologies, and I could talk for hours on just that alone and why we need to move on to the other science, but physics is not done. It's constantly evolving. And to have the focal goals of breakthrough starflight is there. Now, the interesting things here is there's three concepts right there that once were the sole province of science fiction, but in 1988, traversable wormholes, fast and light wormholes, was in the peer-reviewed journal and has since been debated. 1994, warp drives, moving segments of space-time faster than light, and there's actually homework problems in general relativity textbooks for teaching students about that. And 97, the idea of space drives. They're slower than light, but they don't need propellant. And all those were once just science fiction, but now they're a part of normal scientific discourse. And then realizing that with all these things emerging, there was a gap that needed to be filled. And myself and quite a few other volunteers, and somehow I finagled to be able to do this in part of my NASA time, and part on home time too. But this is the first scholarly textbook. And when I say scholarly, I mean it has all the equations and references, and it's thick, and it's at textbook prices. To cover non-rocket space drives, to cover the idea of modifying gravity. Sometimes the term anti-gravity is used, but I really don't like that term. And faster than light travel. And the idea was to give students a realistic starting point of where is the physics today, what are some ideas that have been approached, and what's left to solve. Now, this is just real short, a couple of ideas about space drives. Rather than using propellant on board, what if you could push against the surrounding matter and push the spacecraft in the other way, and extend that to pushing against the entire universe, which then brings to questions about the meaning of inertial frames. And if there's any physicists in the audience whose eyes are beginning to roll back in their head, check out Chapter 3, because it goes into detail about what those issues are, what has been worked, and what remains left to be solved. On the faster than light, unfortunately, I don't have the time to detail them, but here's a number of concepts. The first two are theoretical entities. They're in general relativity. They're in textbooks. There are ways of actually circumventing the light speed barrier. Quantum non-locality, that's an interesting one. It was, in a sense, talked about here before about things are entangled. And even though it's experimentally based, what is the hard part about it is the interpretation of those, because our language of cause and effect over space, where there's a time delay of getting the information, is still not very sophisticated. We are still so biased by our own experiences of seemingly instantaneous communication that it's hard to work out. The hyperspace idea. Hyperspace is actually a real thing in physics, but it's not the hyperspace of the science fiction propulsion. I just wanted to do that. And one of my favorite ideas, the infinite improbability drive, unfortunately that's still fiction. Now, the one thing is that by challenging these things, we're serving humanity. And one thing is that, you know, this gives hope for the future. Earlier talk, I was so glad someone else brought it up so I didn't have to go into the details. We need to get off the planet in order to survive indefinitely. But the other one, and this kind of conveys into some of the things we're saying, is that, you know, if we're conquering frontiers together, hopefully we'll be less likely to have no other option than to conquer each other. So it gives us a peaceful thing to do. And then also the technologies that we would chase to try and make this happen also have implications on Earth. And just real quickly, other things that we do to inform. If you're curious about keeping up with what's going on, this website, Sendari Dreams, keeps up with that. They take peer-reviewed articles and then translate them into more lay terms. If you're interested in joining like an effort, there's this idea of mosaic Earth, where if you take a close-up, that picture is actually made from faces that are sent in. The idea, wouldn't it be cool to put that on the next deep space probe? But the other thing here, I want you to think about colony ships for a while. That is kind of a neutral ground, since they don't exist yet, to actually debate governance models and other things that so frequently argue about in terms of war. And also, it forces the technology to address self-sustaining life support systems, which could certainly be of use on Earth, rather than just deep space flight. And the other thing that's interesting about a colony ship, energy-wise, it's comparably the same level of difficulty as a small but very fast probe. And that's a long discussion to itself. And to close this out, the thing to walk away with. The next time you're out and you look at the stars, there are actually people now working to try and figure out how to make that happen. And because we're reaching beyond the comfort zone of a lot of our peers, if there's breakthroughs out there to be found, we're going to find them first because we're looking where other people aren't. And also in the process, we're going to learn a lot of ways. And if we succeed, we're going to save humanity from extinction. So that's kind of a cool thing. And, and the last thing, our motto ad astra incrementis means to the stars in steps, but where each step is bigger than the preceding one. Thank you.